so let's now move on to vane diffusers. And as we know, for high work coefficient centrifugal compressors, corner separation in vane diffusers is a major issue. And this was also a collaboration between ADT, ETH, Sulzer Turbo, and ABP Turbo. And basically the baseline compressor was tested with a vane diffuser that was then redesigned. And the baseline vane diffuser had prismatic blades, and it had these 25 blades, and the inlet angle was 25 degrees. The diffuser leading edge was at a radius ratio of 1.16 and the trailing edge was at 1.54. So one of the aspects of this diffuser was that when you look at the detailed flow, which was based on stage CFD, then you saw a very big corner separation on the pressure surface near the hub. And their aim was actually to induce this corner separation and try to make this diffuser more compact as well. So now we have already discussed this corner separation in our last webinar on pumps, and this is actually quite a complex phenomenon. So it's not a simple separation, as there is also a very strong positive pressure gradient on the pressure surface. It actually occurs as a result of accumulation of low momentum or low stagnation pressure fluids at the end wall. And then that low stagnation pressure fluid undergoes this positive pressure gradient, and then you get this really huge corner separation. And for redesign, what they actually did was, well, first of all, the meridional geometry, and you can see they actually reduced the radial extent of the diffuser by almost 1/3. So in fact, they went from a radius ratio of 1.54 to 1.4. So they are making the diffuser much more compact. They are lowering the solidity of the diffuser, and they went from 25 blades to 19 blades. So by going to a lower solidity diffuser, they wanted to see if it's possible to achieve the same pressure recovery. And generally, as you know, when you use a lower solidity diffuser, you will lose pressure recovery as compared to the standard diffuser. And they wanted to see whether you can achieve the same level of pressure recovery as the standard diffuser, even though they have actually lowered the solidity considerably. In terms of blade loading, we have already looked at diffusers in the pump webinar, and even though they look very different over here, but we found that actually the same type of loading, which is fore-loaded at the hub after the effect. So they actually get low as on the leading, and they only did this because the baseline diffuser also had a negative incidence, and they wanted to match the choke margin to the standard. And in the design, they also impose a linear variation of the radial velocity. So what you see over here is the measured radial velocity from the impeller going into the diffuser, and this is the tangential. And so the tangential velocity is almost uniform, so they assume almost a uniform variation of tangential velocity, but they did impose a linear variation of the radial velocity from 0.4 at the hub to a lower value of 0.25 at the shroud. And these are actually the non-dimensional velocities, that is B over U tip. So the resulting blade shape is three-dimensional, as you can see here. And what you can see clearly is that we have actually removed the corner separation. And to understand why the corner separation goes away, it's actually a similar mechanism that we saw in the pump webinar. So you create a strong span-wise secondary flows that move the low momentum fluid away from the end wall. And we are also reducing the amount of positive pressure gradient here. And then a combination of these two helps them to eliminate this corner separation. And this is actually the measurement that was done at the ETH facility. And you can see that, in fact, the measurements were done with the original impeller and the original diffuser. So that's the standard or the orange lines. And then with the original impeller and the new diffuser, which is the blue line here. And you can see that at the design point, we are actually getting the same level of pressure recovery, even though we have much lower solidity in the vane diffuser that was designed by the inverse design. At the lower than design flow conditions, the vane, we are actually getting slightly more pressure recovery, and we lose a little bit of pressure recovery at higher than design flow. And generally, this trend is respected all the way across the map. When we look at the detailed flow field inside at the exit of the diffuser, then this is quite interesting. This shows the blockage distribution at point C, best point, and the point A. And basically here, a value of 1 would be equivalent to inviscid flow or zero blockage. And the more the value is higher than 1, the more circumferential non-uniformity you have at the exit of the vane diffuser. And as you can see, that if you compare the blue with the conventional, at all operating points, the inverse design is showing much more uniform flow at the exit compared to the baseline. And so basically the optimum loading distribution for vane diffusers seems to be fore-loaded at the hub and aft-loaded at the shroud. And in fact, this is quite similar to what we have in pump applications as well. And experiments confirm higher or similar level of pressure recovery with lower solidity blades. And this could be quite advantageous when you want, for example, a wide operating range, or perhaps you want to have a more compact design.